Alright, welcome back everybody. In this video we're going to look at the examples from the initial value problems lesson. If you think back to the last lesson on slope fields, what we did at the very end was we took our slope field and then we gave ourselves some condition, the value of a function at a single point, with which we could then draw a specific solution curve. We're going to do the same thing algebraically in this lesson. We're going to start with a differential equation. We're going to have the value of the function at one point, and then we can find one specific solution curve that has that differential equation as its derivative and that function value as a solution to that equation. So here's how we're going to go about this process. We're going to start with the differential equation, and we're going to find the general antiderivative. So the antiderivative of dy dx is y, the antiderivative of 3x squared is x cubed, the antiderivative of 6x is 3x squared, the antiderivative of 8 is plus 8x, and don't forget your constant of integration, because your constant of integration is going to become crucial in these particular problems to finding the particular solution curve. Alright, so now we have this initial condition that y of 1 is 7. So in other words, when x is 1, y is 7. And we can substitute this value into this antiderivative that we found in order to solve for the value of c. Let's see, 1 minus 3 plus 8, that's going to be 6. Subtracting 6 from both sides, we get that c is equal to 1. And so we come up with the solution to this initial value problem, y equals x cubed minus 3x squared plus 8x plus 1. And this is the one and only curve that has dy dx as its derivative and goes through the point 1, 7. So that's what we do when we find an initial value problem. We find the one solution curve that meets all of these characteristics. Let's look at example 2. In example 2, we start with the second derivative. So we're going to... Why am I writing that? We're going to take the antiderivative of the second derivative. So the antiderivative of that is going to be dy dx equals 4x squared plus a constant. And now we're going to use this initial condition, which tells us that when x is 1, the derivative is 11. So I substitute 11 in there for y and 1 for x. And we get that c is equal to 7. And now we have the derivative of the function that we wish to find. And now we're going to go through the antiderivative process again. The antiderivative of dy dx is y. The antiderivative of 4x squared is 4/3 x to the third. Antiderivative of 7 is 7x. Now we have another constant of integration. If you wanted to, you could go through and subscript your constants of integration so that you can keep them straight. Although if we only use one at a time, I have no problem with just repeatedly using the constant of integration c. Alright, so let's see. 4/3 plus 7 is going to be 25 over 3. And then subtracting 25 over 3 from both sides, we get negative 46 over 3 for the value of that constant. And now we can write our equation that is the solution to this initial value problem. And this is the one and only function that has as its second derivative d squared y dx squared equals 8x, that the value of the derivative at 1 is 11, and that the value of the function at 1 is negative 7. Alright, let's go on to example 3. And really, the only way I can make initial value problems more difficult is by making the calculations more difficult in finding our constant, or by going to successively higher order derivatives to start with. In example 3, we start with the third derivative. So we'll go ahead and take the antiderivative of that, which gives us the second derivative. And then we see here that the second derivative is equal to 5 when x equals 1. And so we'll put 5 in here for the second derivative and 1 for x. And we find that our constant is 4. So the second derivative is d squared y dx squared equals x squared plus 4. Then I find the antiderivative of that. The antiderivative of d squared y dx squared is dy dx. It's going to be 1/3 x to the third plus 4x plus a constant. And now we're going to use this portion of our initial condition. The derivative is 4/3 when x is 1. So let's see, 4/3 is equal to 13/3 plus c. Subtracting 13/3 from both sides, we get c equals -3. So dy dx is equal to 1/3 x to the third plus 4x minus 3. And then the antiderivative of that is going to be y. And that's going to be 1/12 x to the fourth plus 2x squared minus 3x plus a constant. And now I'm going to use the last initial condition here. 25 over 12 is equal to 1/12 times 1 to the fourth plus 2 times 1 squared minus 3 times 1 plus c. If we add up everything on the right-hand side, we've got -3, a +2, that's -1, and 1/12, so that's going to be -11/12. Adding 11/12 to both sides, we get that c is equal to +3. And so our particular solution in this case is y equals 1/12 x to the fourth plus 2x squared minus 3x plus 3. And that's the one function that has all of those as conditions. All right, example 4. A rock is thrown downward from the top of a 100-meter tall building at 5 meters per second. How high off of the ground is the rock when after t equals 2 seconds? So what we want to do is we want to find a function for the position of this rock. And we know that it's thrown downward from the top of a 100-meter tall building. So the position at time 0 is equal to 100. With a velocity of 5 meters per second, it's being thrown downward, so that's going to be a negative velocity. So v of 0 equals -5. A lot of power chord issues. Come on. Stay on there. Alright, and the only other thing I need to know to find this function is what my acceleration function is. Because if you remember, acceleration is the derivative of velocity, and so I can take the antiderivative of that to get the velocity function. Well, acceleration, since we're measuring in meters, is a constant -9.8. We're just going to go to one decimal place with that, -9.8. Alright, and now I find the antiderivative of this function. dv dt is equal to -9.8. So the antiderivative of dv dt is v. It's going to be -9.8t plus a constant. And now I'm going to use the initial condition for velocity. So velocity is -5 when t is 0. So my constant is -5. So my function for velocity ends up being -9.8t minus 5. And then since v is the derivative of position, I take the antiderivative of that to get the position function. That's going to be negative 4.9 t squared minus 5t plus a constant. Now the position at 0 is 100, so 100 is equal to all of this stuff. So c is going to be equal to 100, and s is negative 4.9 t squared minus 5t plus 100. And now in order to figure out how high off the ground the rock is after 2 seconds, I'm going to just substitute 2 in here for time and calculate. So we've got negative 4.9 times 2 squared, which is 4, minus 5 times 2 plus 100. And the rock is going to be 70.4 meters off the ground after 2 seconds. Now, those of you who have taken physics, you might recognize that these are your standard kinematic equations. And really, this is where your kinematic equations come from. They all get built from the idea that acceleration is this constant value, and then by taking the antiderivatives and putting initial conditions in, we develop our equations that we utilize for velocity and for position in our physics class. All right? Anyway, that's the end for this video, and actually the end of this unit. See you guys next time. Have a great rest of your day.